Okay, so in this video we're going to look at what effect the temperature has on the rate constant. So if we take sort of a rate equation like this, rate equals K times AB, let's make one up, okay. We increase the temperature, it has no effect on the concentration of A or B. So we do know though the rate increases when temperature increases, so it must affect K. K must increase. So we think back, what we're going to look at is stuff we looked at, a Boltzmann distribution like this. Okay, we know that we've got number of molecules or particles here. Kinetic energy here. The temperature increases, higher temperature, this graph shifts like this. So more particles have energy above the activation energy. So what we're going to look at in this video, this is kind of a qualitative way of saying it. We're going to look at mathematically what is a relationship. And clearly, if we know that the rate increases when temperature increases, it must be the rate constant that increases. So the rate constant must increase as temperature increases, and that's what we're going to look at, is that relationship. Okay, so this is called the Arrhenius equation, and it explains mathematically explains the relationship between K, the rate constant. So this is what this K is here. It's not a new K, don't worry. It's a rate constant K, and this is the Arrhenius equation. So there's two parts to it, really. A stands for the pre-exponential factor. Basically, that is fairly independent to temperature. It basically looks at when two particles collide, what is the probability really of them reacting in terms of irrespective of what energy they've got. So sometimes, if you had a particle, let's say we do a reaction like this. Okay, delta minus there, delta plus on there. Get the hydrogens. Okay, if we want OH minus to react with this, it's got to collide here, hasn't it? That's where the mechanism is. If it approaches from the wrong side, the reaction may not happen. So this is what this factor here looks at. A is looking at the probability of them colliding with the correct orientation. This part here, the exponential factor, accounts for how many particles have sufficient energy above the activation energy. So basically, going back to our Boltzmann distribution, quick one here. This area here, okay, proportionally equals E. So E is hold on a second. E to the power of minus EA over RT. Okay. So E is a number used in maths. It's a bit like pi, for example. I'm not going to go into the details where E comes from, but it's used a lot when we're looking at natural decay and things like that. So its number is 2 point something. Okay, don't worry about that too much now. And it's put to the power of minus EA. So EA is the activation energy, divided by R, the gas constant, which doesn't change, and the temperature, which must be in Kelvin. Okay. So this bit here proportionally represents this bit here. This value here can never really quite get to 1. So the nearer it is to 1, the bigger this area is. So if every single particle reacted, this value here would come out as 1. Right. So we can rearrange this to find different parts. If we know certain things, we can rearrange it to find other parts of the equation. But what we tend to do is rearrange it like so. Okay, this is the logarithmic form. So if you just think about what it was K equals A e to the power of minus EA over RT. if you see this here, ln, that's what's called natural log. Okay, so it's basically the log to the base e, the strange number e. So if we want to get rid of e, we've got to do the natural log of it. So if we do the natural log of both sides, natural log of all of that, like so. Mathematically we can simplify this down. So because these two are times together here, ln, the a and the e, we can change that. So we have ln a plus ln e to the minus ea over rt, and the natural log of e is just 1. Okay, so we can bring that down and we end up with this here. Right, so that is the logarithmic form of it. Now you will get these on your data sheet, but you do need to learn this one well because it's the one we use more. Okay, this one, so one of the previous pages on your data sheets, this one you need to learn. So what do we use it for? Why is this important? Well, we can use it to plot a graph. If you put it into the standard graph form, a straight line graph, where y is ln k, x is 1 over t, the gradient of the graph is minus ea over r, and the y-intercept c is ln a. Okay, so what we're going to do, what we do is we plot on the y-axis ln k, and on the x-axis 1 over t, like so. So if we do that, get a graph like that, it'll come out as a straight line if we've done it properly. And so we've got the ln k on the y-axis, 1 over t, and that's got to be, t's got to be in Kelvin first. On the x-axis, we plot the values, and the gradient will give us minus ea over r, and the y-intercept gives us ln a. So if we wanted to find the value of a, e to the power of ln a will give you a. Okay. If we want to find the activation energy, with the gradient, minus gradient times by r. So there we can see an example. These plots quite often are upside down and back to front because of the nature of the natural log of the k's. Quite often they could be in exponential form up here. The 1 over t is not surprisingly very small. Kelvins are normally in the hundreds, so you do 1 over a number like that, you get very small numbers. So you will have to know how to plot a graph like this at some point. So you can see here then they've gone dx, so they've gone from one point to another, worked out what dx is. Be careful of the values here. Sometimes they might do, rather than doing like that, they might do 3.15 times 10 to the minus 3. So be careful of 10 to the minus 3, it is important. And they've done the d, so we've got dx dy. Okay, the slope is going backwards, if you like, or sloping. It's a negative gradient, so that's why it's minus 1.95. That gives you the gradient, and then they're timesing that by r. It's my data sheet as well. And because r's units are in joules per mole per Kelvin, you get your answer here in joules per mole, but it tends to be more standard, and quite often when the answer they require it in kilojoules per mole, so you divide by 1000.